Feynman's father had no degree and taught him everything. The man who created modern physics education, who invented the most iconic diagrams in all of science, who won the Nobel Prize, who could explain quantum electrodynamics to a freshman and make them feel like they understood the universe. This man was not trained by professors at Harvard. He was not mentored from birth by some aristocratic family of scientists. He was not raised in a home lined with credentials and accolades. No, the most brilliant physics mind of the 20th century was educated, fundamentally, at his core, by a uniformed salesman from Minsk who never went to college. Let that land for a moment. Richard Feynman was born in 1918 to Lucille Phillips, a homemaker, and Melville Feynman, a military uniform salesman. Melville was taught at home, first by his father and then by special tutors. He attended the regular high school in Patch Oak, but never went to college. Although Melville wanted to become a doctor, the family could not afford to support his education. He tried a variety of occupations and finally settled in the uniform business. And yet, this man, this salesman, with no degree and no laboratory and no published papers, would plant the seeds of understanding in a boy who would grow up to reshape physics itself. This is the story of Melville Feynman. And it's not just a story about one brilliant father and one brilliant son. It's a story about what education actually is, what understanding really means, and why the things we call credentials often have almost nothing to do with knowing. Welcome to Physics Explained Simply, and today everything you think you know about how great minds are made is about to change. Before we start, why this story matters. We live in an age that worships credentials, degrees, certifications, titles, published papers, institutional affiliations. These are the currency of modern intellectual authority. We build entire systems, educational, professional, social, around the idea that what you know can be measured by where you studied and what piece of paper hangs on your wall. And look, there's nothing inherently wrong with formal education. Universities are extraordinary institutions. Research departments drive human progress. The collective enterprise of science depends on rigorous training and shared methodology. But here is the trap, and it is a trap that Melville Feynman, a man who sold uniforms for a living, understood better than almost anyone in the history of education. Knowing the name of something is not the same as knowing something. That single idea, that one distinction might be the most powerful insight in the history of learning. And it came not from a professor, not from a dean, not from a published pedagogical framework. It came from a father sitting with his son on a front porch in Far Rockaway, Queens, looking at birds. We're going to unpack that idea today. We're going to follow the thread from Melville's simple lessons to Richard's Nobel Prize, and in the process, we're going to discover something genuinely revolutionary about how the human mind actually learns physics, about how any mind learns anything at all. But first, let's go back to the beginning. The uniform salesman from Minsk, Melville, Arthur Feynman, came to the United States in 1895 as a child from Minsk in Belarusia with his parents. His father, Jakob Feynman, a Lithuanian Jew, had settled in Minsk with his family. Many of the Russian and Polish Jews at that time had a great faith in the new science that was developing, and Jakob Feynman had fallen in with a group of rationalists. Times were hard in Minsk, especially for the Jews, and Jakob, liable with his wife and son Melville, immigrated to America. So here was a family rooted in a tradition that valued rationality, that valued questions, that valued figuring things out for yourself rather than accepting what you were told by authorities who might or might not have your best interests at heart. Melville grew up on Long Island in a modest household. It is clear that his talents were not in business, but rather in science, which was the subject that fascinated him. But he never had the opportunity to make a career from it. Think about that. This was a man who loved science, who burned with curiosity about the natural world, but was born into circumstances that denied him the chance to pursue that love professionally. He couldn't afford college. He couldn't afford medical school. The doors that credentials opened were simply closed to him. This was something of an unsatisfied dream his father held for himself. But as things turned out, this wasn't a forthcoming reality, and by guiding a new son in this direction, he could live his dream vicariously. Now, you might be thinking, okay, so this is just a standard parent lives through their kids story. Tiger dad pushes son to achieve what he couldn't. We've heard that before. But that is not what happened here, not even close. His son did arrive, and Melville dove into his plans with all sincerity. But never would he push Richard along too narrow a path. This is the crucial distinction. Melville Feynman was not a taskmaster. He was not drilling his son with flashcards. He was not demanding perfect test scores or pushing him through accelerated programs. What he was doing was something far more radical, far more subversive, and infinitely more effective. He was teaching his son how to see the tiles on the high chair. Let's start at the very beginning, and I mean the very beginning. A later family legend held that Melville announced in advance that if the baby was a boy, he would be a scientist. Lucille supposedly replied, "Don't count your chickens before they hatch." But Richard's father undertook to help his prophecy along. Before the baby was out of his high chair, he brought home some blue and white floor tiles and laid them out in patterns. Blue, white, or blue, white, blue, white, blue, white, trying to coax the baby to recognize visual rhythms, the shadow of mathematics. Stop. Think about that for a moment. Here is a uniformed salesman, a man with no degree, no training in early childhood development, no pedagogical theory, and he's doing something that modern cognitive scientists now recognize as profoundly effective. He's introducing mathematical thinking before language, before reading, before numbers. He's showing a baby that the world has structure, that things happen in sequences, that patterns exist. He wasn't teaching math. He was teaching the idea that math is possible, that the world is patterned, that order lives underneath chaos if you look carefully enough. And when Lucille, Richard's mother, saw what was happening, she said something like, "Leave the poor child alone. If he wants to put a blue tile, let him put a blue tile." But Melville said, "No, I want to show him what patterns are like and how interesting they are. How interesting they are. Not how useful, not how important for your future career, not how necessary for getting into a good school." He said, "How interesting they are." Melville wasn't training his son. He was inviting him into wonder. And this right here is the key to everything that followed. The dinosaur at the window. As Richard grew, Melville kept doing what he did best, turning abstract facts into vivid, tangible reality. Feynman explained, "When I was a small boy, my father used to sit me on his lap and read to me from the Encyclopedia Britannica, say about the dinosaurs, that this thing was 25 feet tall and its head was 6 feet across and so on. But he would stop always," Feynman recalled. "What does that even mean? Suppose the dinosaur stood in our front yard, then it would be high enough to put its head through the window, but not quite, because the head would be too wide and it would probably break the window apart." That is how Melville translated every numerical fact into pictures, into reality, and Richard thus started to grow an unbound sense of imagination from an early age, thanks to his father. Now let's pause and appreciate the genius of this. 25 feet tall. What does that mean? It means nothing. It's just a number. It's just a label. But a dinosaur sticking its head through your bedroom window, too big to fit, cracking the glass. Now you know something. Now you feel it. Now it's real. This is something Feynman would carry with him for the rest of his life, this instinct to translate the abstract into the physical, to never accept a number until you could feel what the number meant. When he was a professor at Caltech decades later, explaining quantum electrodynamics or the behavior of superfluids or the strange nature of light, he was still doing exactly what his father had taught him in that living room in Queens. He was taking something abstract and making it real, making it vivid, making it land. The Encyclopedia Britannica became Richard's playground. He learnt a great deal of science from Encyclopedia Britannica and taught himself elementary mathematics before he encountered it at school. But it wasn't just the encyclopedia, it was what his father did with the encyclopedia. The constant interruptions, the constant translations, the constant demand. But what does that mean? Imagine if every child heard those 4 words after every fact they learned. But what does that mean? The world would be different, profoundly different. The walk in the woods, learning to notice now. Here is where it starts to get really interesting. Melville would take his son on walks, pointing out things in the natural world such as worms, ants, and birds, and explain their behavior in nature. He would emphasize to young Richard that the naming conventions and scientific jargon that so many seemed to get caught up in was much less important than observing and truly understanding what was going on in the natural world. This wasn't casual strolling. This was education in its purest and most ancient form. A father and a son walking through the world together, looking at things, noticing things, wondering about things. Feynman remembered those walks vividly, decades later. He recalled that his father would tell him about everything: the stars, the bugs, geometry, the way birds fly, the way the oceans work. There was always talking, always discussing, always wondering. But the key, the absolutely critical key, was what his father was not doing during these walks. He was not naming things, or rather, he was demonstrating that naming things is not the same as understanding them. And this leads us to perhaps the most famous story in all of science education. The bird that changed everything. Feynman told this story many times in many different ways throughout his life. It never lost its power. Let me set the scene. Richard is a young boy. A weekend has passed. The fathers in the neighborhood have been home spending time with their kids. Monday arrives. The fathers go back to work. The kids go out to play in a field. And another boy points to a bird and says, "See that bird?" "What kind of bird is that?" Young Richard says, "I haven't the slightest idea." The boy says, "It's a brown-throated thrush." Your father doesn't teach you anything. But here is the twist. Here is the revolution packed into a child's playground exchange. It was the opposite. He had already taught me. "See that bird?" he says. "It's a Spencer's warbler." I knew he didn't know the real name. Well, in Italian, it's a chuto lapitida. In Portuguese, it's a bom da pita. In Chinese, it's a chung long ta. And in Japanese, it's a katano takeda. You can know the name of that bird in all the languages of the world. But when you're finished, you'll know absolutely nothing whatever about the bird. You'll only know about humans in different places, and what they call the bird. Do you hear that? Do you really hear that? A man who sold uniforms for a living, a man without a college degree, articulated one of the deepest philosophical insights in the history of epistemology: the difference between knowing the name of something and knowing something. This isn't just a cute anecdote. This is a fundamental critique of how most education works. Think about your own schooling. How much of it was naming, memorizing terms, memorizing definitions, memorizing labels? How much of it was actually understanding what was happening underneath the labels? If I say to you right now, gravity is the curvature of space-time caused by mass and energy, have you learned something? You might feel like you have. The sentence sounds impressive. You can repeat it at a dinner party. But can you feel it? Can you picture it? Do you know what it means for time to bend? For space to curve? For mass to warp the fabric of reality? Or do you just know a name? Melville Feynman, the uniform salesman, understood this distinction at a bone-deep level, and he passed it on to his son like a gift wrapped in wonder. The ball in the wagon, a lesson in inertia. But Melville didn't just teach Richard to question names. He taught him to observe, and then to explain what he observed. There's a wonderful story about a little red wagon with a ball in it. Young Richard notices something strange. When he pulls the wagon forward, the ball rolls to the back. When he stops suddenly, the ball rolls to the front. He runs to his father and tells him about it, and here's what Melville does. He doesn't just say, "That's called inertia." He engages with the observation. He explores it. The general principle is that things which are moving tend to keep on moving, and things which are standing still tend to stand still, unless you push them hard. This tendency is called inertia, but nobody knows why it's true. He didn't just give me the name. He went on to say, if you look from the side, you'll see that it's the back of the wagon that you're pulling against the ball, and the ball stands still. As a matter of fact, from the friction it starts to move forward a little bit in relation to the ground. It doesn't move back. I ran back to the little wagon and set the ball up again and pulled the wagon. Looking sideways, I saw that indeed he was right. Relative to the sidewalk, it moved forward a little bit. That's the way I was educated by my father. With those kinds of examples and discussions, no pressure, just lovely, interesting discussions. There are so many layers to unpack here. First, Melville gives the concept before the name. He explains what is happening. Then, almost as an afterthought, he says, this tendency is called inertia. The name comes last, not first. In school, we typically reverse this. We introduce the term, then try to explain it. Melville understood intuitively that real learning works in the opposite direction. Second, he says nobody knows why it's true. This is staggering. This is a father telling his child that science doesn't have all the answers, that there are mysteries, that the universe is not a textbook with an answer key at the back. He's teaching his son that it's okay not to know, and that the not knowing is itself part of the beauty. Third, he changes the child's frame of reference. Look from the side. Look at it differently. See it from a new angle. This is exactly what physicists do. This is exactly what Einstein did when he imagined chasing a beam of light. This is what Feynman himself would later do when he imagined positrons moving backward through time. And fourth, and this is perhaps the most important part of all, Melville sends the boy back to check. He doesn't just expect Richard to accept the explanation. He expects him to verify it, to observe again, to test the claim against reality. This, right here, in a living room in Queens, with a wagon and a ball. This is the scientific method, not as a list of steps in a textbook, not as a procedure to follow in a lab, but as a living, breathing way of engaging with the world, taught by a man who never set foot in a university, the man behind the uniform. But here's where it gets even more interesting. Melville didn't just teach his son about science. He taught him about human nature, about authority, about the dangerous illusion of credentials. Remember, Melville Feynman sold uniforms. He sold them to police officers, to postal workers, to military officials. He saw men before they put on the uniform, and he saw them after. And what he noticed was that the uniform changed people's perception, but it didn't change the man. Melville was in the garment business. He sold uniforms to police officers, postal workers, and the like, and he taught Richard never to take formal authority too seriously. He had, after all, seen the important figures before they acquired their fancy uniforms. Feynman told this story beautifully. His father would open the newspaper, find a picture of some dignitary, a general, the Pope, whoever, surrounded by people bowing or saluting, and he would say to little Richard, "Now, look at these humans. Here is one human standing here, and all these others are bowing." And then his father would ask the devastating question, "Now what is the difference?" "This one is the Pope." And he'd say, "The difference is epaulets." Of course not in the case of the Pope. But if he was a general, it was always the uniform, the position. But this man has the same human problems. He eats dinner like anybody else. He goes to the bathroom. He has the same kind of problems as everybody. He's a human being. It was always the uniform that gave the person authority. Otherwise, he was like anyone else. He, by the way, was in the uniform business. So he knew what the difference was with the uniform off and the uniform on. It was the same man for him. Now, you might think this is a nice lesson in humility and leave it at that. But this lesson had profound consequences for physics. Think about what this teaching does to a young mind. It creates a person who does not bow to authority, a person who evaluates ideas based on their merits, not based on who said them, a person who, when told by the greatest physicist in the world that something is true, will say, "Yes, but is it really? Let me check." This is exactly what Feynman did over and over again throughout his career. In Los Alamos, Feynman was assigned to Hans Bethe's theoretical division, where he made enough of an impression to become a team leader. He was also sought out for one-on-one discussions with Niels Bohr, as most of the other physicists were too in awe of Bohr to have honest discussions and disagreements about physics. Feynman had no such inhibitions. Do you see the thread? A uniformed salesman teaches his boy that the general is just a man in fancy clothes. Decades later, that boy walks into a room with Niels Bohr, one of the founding fathers of quantum mechanics, a scientific colossus, and treats him as an equal, not out of arrogance, out of an understanding that ideas do not become true because important people say them. Ideas become true because nature says so. This is the foundation of all good science, and it was taught in a living room by a man without credentials opening a newspaper. The mother's gift. Now I would be doing a disservice if I didn't pause here to talk about Lucille Feynman. Because Melville was not the only force shaping young Richard's mind. Feynman's father, Melville, provided the gift of knowledge and seriousness, while his mother, Lucille, gave the gift of love and storytelling. His mother, Lucille, instilled into Richard a quality that, although less obvious, was nevertheless of equal importance to his future success as an explorer. That critical quality was a powerful sense of humor. Not to be dismissed or taken lightly, it was Lucille's brand of humor that empowered him. While Melville provided Richard the tools to choose his own path, Lucille taught him how to laugh out loud at self-importance, giving him the all-important courage to step onto the path. You see, knowledge without courage is just a hobby. You can understand the world perfectly. But if you're afraid to say what you see, afraid to challenge the accepted view, afraid to look foolish, then your understanding never reaches anyone. Lucille gave Richard the ability to be fearless, to laugh, to not care what other people thought. And when guests would come to the house and see the chaos that Richard's experiments caused, the wires, the chemicals, the occasional small explosion, the smoke stains, and they would ask Lucille how she could possibly tolerate it, she would simply say, "It's worth it. It's worth it." 3 words. And in those 3 words, an entire philosophy of parenting, of education, of human development. The messes are worth it. The noise is worth it. The uncertainty and the chaos and the disruption, they are worth it. Because something real is being built here, something that no tidy, quiet, orderly classroom could ever produce. Both of his parents were a formidable combination to guide him his whole lifetime. Now, let's talk about physics, what Melville's lessons really mean. Here's where we connect Melville's kitchen table philosophy to the deepest questions in physics. Because everything his father taught him, the patterns, the observations, the distrust of naming, the insistence on understanding, shaped the specific way Feynman would later do physics. Let's take the most famous example. In the late 1940s, physics had a problem. Quantum electrodynamics, the theory that describes how light and matter interact, was giving physicists infinite answers, literally infinite. When they tried to calculate the probability of an electron doing something as simple as scattering off another electron, the mathematics would spiral off into infinity. Nonsense answers. The theory seemed broken. Now, the conventional approach at the time, championed by Julian Schwinger at Harvard, was to wrestle this problem with extremely sophisticated mathematics. Schwinger's solution was brilliant. It was also incredibly dense, filling pages and pages with abstract formalism that only a handful of people in the world could follow. And then there was Feynman. Feynman would use drawings to simplify a difficult concept, which helped him win a Nobel Prize later on. While Julian Schwinger's formulation of quantum electrodynamics was mathematically superior and far more complex to work with, Feynman's drawing approach broke the whole thing down into simpler diagrams. Feynman drew pictures. He literally drew little pictures, what we now call Feynman diagrams, of particles moving through space and time, interacting, exchanging forces. Feynman developed a pictorial representation scheme for the mathematical expressions describing the behavior of subatomic particles, which later became known as Feynman diagrams and remains widely used. Where did this instinct come from? Where did a theoretical physicist get the idea that you could solve the deepest problems in nature by drawing pictures instead of writing equations? From a high chair in Queens, from blue and white tiles, from a father who said, "Suppose the dinosaurs stood in our front yard." He taught Richard to visualize concepts by showing him tiles with geometric patterns before he could even read. Indeed, visualization would become a key tool for Feynman. Feynman didn't think in symbols. He thought in images. He imagined what the electrons were doing. He put himself in the scene. When he looked at an equation, he didn't see abstract marks on paper. He saw particles dancing, photons bouncing, waves interfering. He saw a reality, and this ability, this astonishing ability to visualize the invisible, can be traced directly back to a uniformed salesman sitting his baby boy in a high chair and laying out tiles in patterns of blue and white. Imagine if. A thought experiment. Let me offer you a thought experiment in the spirit of Feynman himself. Imagine 2 children. Both are bright. Both are curious. Both are born in the same year, in the same city. Child A is enrolled in the best schools. He has tutors and textbooks and structured curricula. Every concept is introduced with its proper name first. Every lesson has clearly defined objectives and standardized assessments. He learns that science is about memorizing facts, passing tests, and moving to the next level. Child B has a father who sells uniforms. His school is a front porch and a vacant lot. His textbook is the Encyclopedia Britannica, interrupted every other sentence. His curriculum is whatever they happen to notice on a walk through the neighborhood. He learns that science is about asking questions that nobody can answer, about looking at the world and seeing something nobody else sees, about translating numbers into dinosaurs breaking through windows. Now, which child becomes a Nobel Prize winning physicist? Obviously, the answer is more complicated than this simple scenario suggests. Feynman was also extraordinarily talented. He had access to good schools. He had a community that valued education. He had the immense privilege of growing up in a time and place where a bright Jewish kid from Queens could, despite real barriers of prejudice, eventually reach MIT and Princeton. But here's what I want you to take from this thought experiment. The formal education came later. The foundation, the bedrock, the deepest layer of how Richard Feynman thought, was laid by a man with no credentials, using tiles and walks and newspaper clippings and a ball and a wagon. Feynman's teaching, the legacy passed forward. And this brings us to perhaps the most beautiful part of the story. Because Richard Feynman did not keep his father's lessons to himself, he became, arguably, the greatest physics teacher who ever lived. Throughout his career, Feynman was dedicated to making complex scientific concepts accessible to the public, earning him the nickname, the Great Explainer. Feynman has been called the Great Explainer. He gained a reputation for taking great care when giving explanations to his students and for assigning himself a moral duty to make the topic accessible. His principle was that if a topic could not be explained in a freshman lecture, it was not yet fully understood. Read that last line again. If a topic could not be explained in a freshman lecture, it was not yet fully understood. This is Melville's philosophy, reborn. This is the dinosaur in the front yard principle applied to the highest levels of theoretical physics. If you can't translate it into something real, something that a person can see and feel and imagine, then you don't actually understand it yet. You just know its name. When Feynman taught his legendary lectures at Caltech in the early 1960s, lectures that were later published as the Feynman Lectures on Physics and became one of the most celebrated physics textbooks ever written, he was doing exactly what his father had done. He was taking abstract concepts and making them vivid, making them physical, making them real. He didn't start a discussion of gravity by writing down equations. He started by asking you to imagine what it would feel like to be in a box floating in space. He didn't introduce thermodynamics with abstract definitions of entropy. He invited you to think about what happens when you stir cream into your coffee and wondered aloud why you can never unstir it. Every single one of his lectures has the fingerprints of Melville Feynman all over it. The anti-credential. Why Melville could do what professors could not now. Let's address something that might be nagging at you. You might be thinking, sure, this is a nice story, but isn't it also kind of obvious? Doesn't every good parent teach their kids to be curious? Maybe. But here's what's not obvious. Melville's lack of formal credentials may have actually been an advantage. Think about it. A professor of physics, trained in the formal methods of the discipline, steeped in its jargon and conventions, might introduce a concept the proper way, starting with definitions, moving to equations, building toward formal understanding. This is how physics is taught in universities, and for many purposes, it works fine. But Melville didn't know the proper way. He didn't have the academic vocabulary. He didn't have the formal framework. All he had was his own burning curiosity and his desire to share it with his son. And so he was forced, by his own limitations, to do something that most trained teachers never do: explain things from scratch, in his own words, using his own images, without the crutch of jargon. And in doing so, he stumbled onto a method of teaching that turns out to be far more effective for building deep understanding than the traditional approach. This is, in fact, exactly what the Feynman technique, a learning method named after Richard, is all about. There is a way to test whether you understand the idea or only know the definition. It's called the Feynman technique, and it looks like this. Without using the new word which you have just learned, try to rephrase what you have just learned in your own language. Can you explain it without the jargon? Can you explain it to a child? Can you explain it using a dinosaur in a window? If not, you don't understand it yet. Melville, by necessity, always explained things without jargon, because he didn't have the jargon. And in doing so, he taught his son that jargon was never the point. Understanding was the point. The depression, the sacrifice, and the visit to MIT. Now let's talk about something less romantic, but equally important: money. We weren't too well off. At that time, my father was making about $5,000 a year. This was in the 1930s. It was a period of depression. The Feynmans were not wealthy. They were a middle-class family navigating the Great Depression, and making the decision to send Richard to a university, to MIT, was a genuine financial sacrifice. Because Feynman had only a small scholarship at MIT, and his parents had worked very hard to send him there, he tried to augment his finances by working with a professor on research projects. And then came a moment that reveals everything about Melville Feynman as a father. His father visited MIT in Richard's senior year to ask Morse whether it was worthwhile for Richard to attend graduate school. Morse told Melville that Richard was the brightest undergraduate student he had ever encountered. Picture this: a uniformed salesman, a man who never went to college himself, traveling to the Massachusetts Institute of Technology to ask a professor whether his son is good enough. This man who taught his boy to distrust authority, who taught him that uniforms and titles mean nothing, is walking the halls of one of the most prestigious institutions in the world, and he is doing it not out of intimidation, but out of love. Out of a simple, practical desire to make sure his son is on the right path. And the professor tells him, "Your son is the brightest student I have ever encountered." Imagine what that must have felt like. For Melville, for the boy from Minsk who couldn't afford medical school, who spent his life selling uniforms, who gave his son tiles instead of degrees, walks instead of textbooks, questions instead of answers. Your son is the brightest student I have ever encountered. The deeper lesson, what understanding really is. Let's go deeper now. Let's talk about what Melville was really teaching at the most fundamental level. There is a distinction in philosophy of science between two kinds of knowledge. One is propositional knowledge, knowing that something is the case. The speed of light is 186,000 miles per second. Electrons have negative charge. The universe is 13.8 billion years old. These are facts, labels, names. The other is what philosophers call understanding, knowing why and how something is the case. Understanding isn't about memorizing the answer. It's about seeing the connections, feeling the logic, being able to derive the answer from first principles, or at least to explain it without leaning on someone else's words. Melville, who had no idea he was doing philosophy of science, was training his son exclusively in the second kind of knowledge. He never cared about the name of the bird. He cared about what the bird was doing and why. He never cared about the word inertia. He cared about what the ball was doing in the wagon and how to see it differently. And when Richard grew up and became a physicist, this training manifested in an extraordinary way. Feynman had a legendary habit of deriving things from scratch. Instead of looking up formulas, he would figure them out himself. Instead of memorizing proofs, he would construct his own. His colleagues would sometimes be astonished to discover that Feynman had independently re-derived results that had taken other physicists years to establish. This wasn't showing off. This was how he understood things. He didn't feel he truly knew something until he had built it himself from the ground up. Until he had, in a sense, translated it, just as his father translated the height of a dinosaur into a beast pushing its head through the bedroom window. The pecking birds, learning to ask, why? Let me tell you one more story from those walks, because it illustrates something that most people miss about the Feynman method of learning. On one of their walks together, Melville pointed out birds that were pecking at their feathers. He asked young Richard, "Why do you think they do that?" Richard, 10 or 11 years old, made a guess. Maybe their feathers get ruffled when they're flying. And here is what his father did. He didn't say, wrong. He didn't say, the correct answer is. He did something much more powerful. He tested the hypothesis. He then said, if that were the case, they would peck more when they just landed after they flew. And after they got straightened out, walking around, they wouldn't peck so much. Do you see what just happened? Melville took his son's guess and derived a testable prediction from it. If feathers get ruffled during flight, then birds should peck more right after landing. They could go watch and check. This is hypothesis testing. This is the scientific method, not as a list of steps on a poster in a classroom, as a living conversation between a father and son on a walk through the neighborhood. And it was after these discussions about pecking birds, about lice on feathers, about how wherever there is a food source, some organism evolves to exploit it, that Feynman recalled his father's approach with those simple, devastating words. No pressure, just lovely, interesting discussions. Lovely, interesting discussions, not lectures, not assignments, not tests, discussions. Thought experiment 2. The classroom that doesn't exist. Imagine a classroom where this is how every subject is taught. Imagine a science class where the teacher starts not with definitions but with observations, where students are taken outside to look at the world before they open a textbook, where the first question is always, "What do you notice?" and the second question is always, "Why do you think that happens?" Imagine a physics class where inertia is introduced not as a vocabulary word to be memorized, but as a puzzle to be solved with a ball and a wagon, where gravity is experienced before it is named, where the speed of light is felt before it is quantified. This is the classroom Melville Feynman built. It had no walls. It had no curriculum. It had no assessment rubric. It had a man who loved science and a boy who was learning to love it too. And it produced one of the greatest physicists in human history. Now, you might say, that can't scale. You can't build a school system around fathers taking walks with their sons. And you'd be right. You can't replicate Melville Feynman. You can't systematize wonder, but you can learn from him. You can adopt his principles. You can start with observation before definition. You can translate numbers into images. You can ask, what does that mean, after every fact. You can distinguish between knowing the name and knowing the thing. Every teacher can do this. Every parent can do this. Every person who has ever wanted to understand something can do this. The Nobel Prize and the epaulets in 1965. Richard Feynman shared the Nobel Prize in Physics with Julian Schwinger and Shinichiro Tomonaga for their work on quantum electrodynamics. When reporters called him in the early morning to tell him the news, he was characteristically unimpressed, because his father had taught him what honors really are. When questioned if his work was worthy of a Nobel Prize, he said, "I don't like honors. Honors is epaulets. Honors is uniforms. My papa brought me up this way. I can't stand it. Honors bother me." For him, the true honor was in the observation that other people used his work and derived inspiration from it. Those were the real things, Richard added. Honors is epaulets. Honors is uniforms. My papa brought me up this way. Do you see how deep the thread runs? The uniform salesman who taught his son that a general is just a man in fancy clothes had raised a man who saw a Nobel Prize as just another uniform. The prize wasn't the point. The understanding was the point. The work was the point. The joy of figuring things out was the point. I don't see that it makes any point that someone in the Swedish Academy decides that this work is noble enough to receive a prize. I've already got the prize. The prize is the pleasure of finding the thing out, the kick in the discovery, the observation that other people use my work. Those are the real things. I've already got the prize. The prize is the pleasure of finding the thing out. That sentence, that single luminous sentence, is Melville Feynman's greatest achievement, not because he said it, Richard said it, but because he made a person who could feel it, who could mean it, who could stand in front of cameras and reporters and the weight of institutional recognition and say, "I've already got the prize." The prize was always the understanding, the wonder, the moment when the ball in the wagon starts to make sense. The moment when you realize the dinosaur would break the window. That is the prize. It was always the prize. The death of Melville and the weight of loss. Melville Feynman suffered a stroke on October 7th, 1946, and died the next day. Richard signed his father's death certificate, his second in less than 2 years. The first had been upon the death of Arlene in the summer of 1945. Melville died suddenly on October 8, 1946, around the same time when Arlene, Feynman's first wife, had passed away. Richard suffered from depression as a result and could not continue doing physics for some time. It was too deep a sorrow. In the span of just over a year, Richard Feynman lost the two people who had shaped him most profoundly. his wife Arline, and his father Melville. The grief was devastating. The man who could solve the most complex equations in physics, who had helped build the atomic bomb, who could crack safes and play bongo drums and debate Nobel laureates, this man was brought to his knees by loss. He couldn't do physics. The fire had gone out. With his research stalled, he got back into solving physics problems for fun rather than utility. One famous example was that of a spinning and nutating disk, which he cracked after seeing someone throw a dinner plate in the Cornell cafeteria. He claimed this inspired him to work with equations of rotations when thinking about electron spin, ultimately proving useful to his Nobel Prize-winning work in quantum electrodynamics. And look at how he came back. Not through discipline, not through obligation, through play. Someone threw a plate in a cafeteria and Feynman watched it wobble, and he thought, that's interesting. Why does it do that? That is Melville's voice, echoing through the decades. That is a father, now gone, still teaching his son to notice, to wonder, to follow the thread of curiosity wherever it leads. The wobbling plate led to equations of rotation. The equations of rotation connected to electron spin connected to quantum electrodynamics, and quantum electrodynamics connected to a Nobel Prize. All because a man who sold uniforms had once taught his boy that the most important thing you can do is look at the world and ask, what does that mean? Joan, the other Feynman scientist, and let's not forget that Melville's influence didn't stop with Richard. Melville, who never himself had the opportunity to make a career in science, encouraged both his son and daughter, Joan, 9 years younger than Richard, to take up science. This was male-oriented, to be sure, but at the time a girl wouldn't have been reasonably expected to get past the guards at the gates of academia. Richard's younger sister, Joan, got past the guards anyway, and became a very productive astrophysicist. Joan Feynman went on to become a distinguished astrophysicist in her own right, making important contributions to the study of the aurora borealis and solar wind particles. She carried her father's lessons too, the curiosity, the irreverence, the delight in understanding rather than naming. Two scientists, one father, no degree. The broader principle, education as invitation. Let's zoom out now and think about what all of this means for how we think about education, about learning, about what it means to truly know something, the standard model of education. And I'm using standard model deliberately because it's a term we use in physics, and in education, the standard model is just as hard to challenge. The standard model assumes that knowledge flows downhill, from experts to novices, from credentialed authorities to uncredentialed learners, from institutions to individuals. And to some extent this is true. Expertise is real. Training matters. You don't want a self-taught amateur designing the bridge you drive across every morning. But Melville Feynman's story reveals something that the standard model misses. The most important thing a teacher can do is not to transfer information. It is to kindle a flame, to create in the student's mind a burning desire to understand, to make the student see that the world is interesting, not because a textbook says so, but because it actually is. You can have all the credentials in the world and fail at this. You can have no credentials at all and succeed spectacularly. Because the best teaching isn't about what the teacher knows. It's about what the teacher makes the student want to know. Melville Feynman never explained quantum mechanics. He never discussed the fine structure constant or the path integral or the renormalization problem. He probably couldn't have defined any of these things, but he made his son want to understand everything. He gave him the tools: visual thinking, healthy skepticism, observational discipline, the distinction between naming and knowing. And then he let the boy's own curiosity do the rest. Thought experiment 3. What would Melville do? Here is your challenge, your homework if you like. Though Melville would never have called it homework. Pick any concept in physics, any one. Gravity, entropy, quantum superposition, wave-particle duality, the expansion of the universe, whatever interests you. Now ask yourself, can you explain this concept without using any technical jargon? Can you translate the numbers into images? Can you make someone feel what the concept means, not just know what it's called? Can you do what Melville did with the dinosaur? Can you put it in someone's front yard? If you can, you understand it. If you can't, if you find yourself reaching for terminology, for names, for labels that substitute for understanding, then you have more work to do. And that's fine. That's wonderful, actually. Because now you know exactly where your understanding ends and the naming begins, and you can start the real work of learning. The work that Melville knew how to do better than almost anyone who has ever lived. The science of learning. What modern research tells us. It turns out that modern cognitive science has vindicated Melville Feynman rather thoroughly. Researchers in learning science have consistently found that deep understanding, the kind that transfers to new situations and persists over time, is built not through rote memorization of facts and definitions, but through active construction of mental models, through visualization, through analogy, through connecting new information to existing understanding. When Melville translated 25 feet tall into a dinosaur at the window, he was doing something that cognitive scientists now call embodied cognition, grounding abstract information in physical sensory experience. When he asked, "What does that mean?" he was prompting what researchers call elaborative interrogation, one of the most effective study strategies ever documented. When he sent Richard back to the wagon to check the observation, he was implementing what we now call active learning. When he gave the concept before the name, he was following what educational researchers have found to be a far more effective sequencing than the traditional definition-first approach. Every single thing Melville Feynman did in his kitchen and on his walks has been confirmed by decades of rigorous educational research. And he did it by instinct, by love, by his own frustrated passion for a scientific career he was never allowed to have. The paradox of credentials. Here is the beautiful paradox at the heart of this story. The most influential physics teacher of the 20th century was not a teacher at all. He was a student who became a teacher, Richard Feynman. And his most influential teacher was not a professor or PhD or researcher. He was a uniform salesman who never went to college. The man with no credentials produced the man who earned every credential. And the man who earned every credential spent his life telling people that credentials don't matter, that honors are epaulets, that the name of the bird tells you nothing about the bird. This is not an argument against formal education. It's an argument for something deeper than formal education. It's an argument for the kind of understanding that no institution can confer and no degree can certify, the kind that lives in the way you see the world, in the pause between hearing a fact and asking, "But what does that mean?" That pause is everything. That pause is where Feynman diagrams come from, where Nobel Prizes come from, where the pleasure of finding things out comes from. And that pause was a gift from a man named Melville, who came to America as a boy from Minsk, who sold uniforms to policemen and generals, and who knew in his bones, without any degree to prove it, that the most dangerous thing in the world is to confuse the name of something with the thing itself, the legacy that lives in the end. What did Feynman gain most from his father? One can say, his childlike curiosity that he maintained throughout his life. But more importantly, the bond that they shared was more that of a loving teacher and a student. Feynman learned from his dad how to think, not what to think, not what to think. How to think, not what to think. That is the entire philosophy. That is the seed from which everything grew. Raised in Depression-era Rockaway Beach, physicist Richard Feynman was irreverent, eccentric, and childishly enthusiastic, and every one of those qualities traced back, in one way or another, to a father who sold uniforms and dreamed of science. Today, millions of physics students around the world learn from the Feynman lectures. Thousands of scientists use Feynman diagrams every day. The Feynman technique is taught in study skills courses from Cambridge to Caltech. Feynman's approach to science, visual, playful, skeptical, joyful, has become one of the dominant paradigms in physics education. And behind all of it, behind the Nobel Prize and the lectures and the diagrams and the technique, stands a man who never set foot in a university, a man who brought home tiles for his baby, who walked with his son and looked at birds, who opened the newspaper and said, "Now, look at these humans." Feynman always remained very proud to admit that he had been trained by his father. What this means for you. Here's the thing. You don't need a degree to understand the universe. You don't need credentials to ask the right questions. You don't need institutional approval to look at the world with wonder. You need curiosity. You need the willingness to ask, "But what does that mean?" You need the courage to say, "I don't know," even when everyone around you seems certain. You need the discipline to observe before you name, to feel before you define, to understand before you memorize. These are not things that universities teach. These are not things that any formal program can install in you. These are habits of mind, habits of heart, really, and they can be cultivated by anyone, at any time, in any place. A father sitting with his child on a front porch, a friend pointing out something strange in the sky, a stranger on the internet sharing a video about physics. Curiosity does not require credentials. Wonder does not require permission. Understanding does not require institutional approval. It requires only this: the willingness to look at the world and to see it, really see it for what it is. The final lesson, the pleasure of finding things out. Feynman once said that he was like someone who was given something wonderful when he was a child, and he's always looking for it again. I've been caught, so to speak, like someone who was given something wonderful when he was a child, and he's always looking for it again. I'm always looking like a child for the wonders I know I'm going to find. Maybe not every time, but every once in a while. The something wonderful, the gift, the thing that was given to him when he was small. It wasn't knowledge. It wasn't information. It wasn't facts or equations or the names of birds. It was the feeling of understanding, the pleasure of finding things out, the electric thrill of watching a ball in a wagon and suddenly seeing, really seeing, how the universe works. Melville Feynman gave his son that feeling over and over again, on walks and at the kitchen table, with tiles and encyclopedias and newspaper pictures, through lovely, interesting discussions with no pressure and no agenda other than the pure, intoxicating joy of figuring things out. And Richard Feynman spent the rest of his life chasing that feeling, finding it in the mathematics of quantum electrodynamics, in the wobble of a dinner plate, in the behavior of ants on his bathroom floor, in the structure, subatomic reality. He chased it all the way to a Nobel Prize, all the way to a legacy that will outlast us all. And he got it all from a man who sold uniforms for a living. So here's what I want you to take with you today. The next time someone tells you that you need a degree to understand something, remember Melville Feynman. The next time someone hides behind jargon and expects you to be impressed, remember the bird. The next time you hear a fact and feel yourself nodding along without really understanding, stop. Stop and ask the question that a uniformed salesman from Minsk taught his son to ask. The question that changed physics forever. But what does that mean? Because that question, that simple, humble, devastating question, is the beginning of everything. It was the beginning of everything for Richard Feynman, and it can be the beginning of everything for you. Thank you for watching Physics Explained Simply. If this story changed the way you think about learning, about understanding, about what it really means to know something, then share it with someone who needs to hear it. Someone who thinks they're not smart enough. Someone who thinks they don't have the right credentials. Someone who has forgotten that the universe is interesting. Remind them of the man who sold uniforms, and the boy who looked at birds, and the difference between knowing the name of something and knowing something,